let's consider a Ferris wheel of radius r. O designates the shaft center of the Ferris wheel. And it's turning with period t. And so specifically, let's say that r is equal to 5 meters and that t is equal to 5 seconds. And let's say that there's a 75 kilogram person sitting in a seat going around on this Ferris wheel. So what I'd like to do is I'd like to find the person's apparent weight at the top of the Ferris wheel and at the bottom of the Ferris wheel. Now remember, apparent weight means the reading on a scale of a scale on which this person is sitting. So to start things off, let's draw a force diagram at the top of the Ferris wheel and at the bottom of the Ferris wheel. You'll notice that at the top of the Ferris wheel, there's two forces acting on the person. A downward weight of mg and an upward normal force n sub t. I'm letting the t stand for top. But by Newton's second law, I know that mg has to be bigger than the normal force because the acceleration has to be towards the center. Always true for UCM. On the other hand, at the bottom of the Ferris wheel, I know that the normal force pushing up on the person has to be larger than mg to give a net force in the same direction as the acceleration, because the acceleration again has to be pointing towards the center because it's UCM. So let's assume a coordinate system y pointing in the upward direction as I have shown, and then let's write down Newton number 2 in the y direction for, first of all, the top of the Ferris wheel. And so I'm going to book the signs to be positive if they're up and negative if they're down. And so that would mean I would have nt minus mg is equal to minus m times at. Minus because a sub t is pointing down. I'm assuming a is pointing down. So if I solve this for n sub t, I get n sub t equals m times a sub g minus m times g minus a sub t. G minus a sub t being in the parentheses. I know that a sub t is equal to r omega squared. And so since I know what the period is, I can compute what omega is. Omega is 2 pi rads over 5 seconds, which comes out to be 1.26 rads per second. That means n sub t is 75 kilograms times the quantity of g, 10 meters per second, minus r, 5 meters, times omega squared, 1.26 inverse seconds squared. Again, I've dropped rads here because rads are going to disappear. So this computes out to be 2.06 meters per second times 75 means that the normal force acting on the person at the top position is 154.7 newtons. And that is their apparent weight by Newton's third law. Look back at the speed bump problem where I talk about the segue, the connection between the normal force and the reading on the scale. And so if I take the normal force and I divide by mg, that's going to be the percent of their weight, percent that the apparent weight is of the weight, and it's roughly 1/5, 21% to be more precise. At the bottom, the Newton number 2 equation is n sub b minus mg is equal to m times a sub t. Now a sub t here is positive. It's pointing in the positive direction of the y-axis that I'm assuming, and so I'm going to bookkeep this as a plus sign. If I solve for n sub b, now I get m times g plus a sub t. And so now you can see immediately that the normal force at the bottom, both from the picture and from the equation, is going to be bigger than the person's weight. So the normal force is 75 kgs times the acceleration of gravity plus the same quantity that we computed above. And if you work that out, it's 17.9 4 meters per second times 75 kgs gives 1345.4 newtons. And the ratio of the normal force, which is the same as the apparent weight of the person, to their weight, is roughly 180%. Okay, so problem for you. For what period will the apparent weight be 0 newtons at the top? And so even before you get started with this problem, we just finished doing t equals 5. So is the t going to be bigger than 5 or is it going to be less than 5? See if you can um, use some intuition to guess which way the t is going to go to make the normal force at the top, which is the same as the apparent weight at the top, head to 0.